Okay, so chapter 4 kind of gets us into something a little bit different. We're looking at matrices. And the question becomes is how are matrices used to organize data? And what operations can be done? Now, matrices I think a lot of you are going to like. I think it's just going to take a little bit of time for you to get used to them. Okay? There's a lot of good things, and I think that you'll find them to be a little bit easier than some of the other stuff we've done, especially as we get started. Okay? So, as we look at these, a matrix is a rectangular array of numbers enclosed in brackets. Okay? Literally, that's all it is. It's a way of organizing some numbers. Okay? Your numbers are organized into rows and columns. Okay? Rows meaning the horizontal part, columns meaning the vertical part. Okay? Hope that's something you know, but if not, that's something you're going to need to be able to figure out. Rows horizontal, columns vertical. Okay? There's some other keywords for matrices that we need to talk about. First one is the dimension. The dimension is given as m by n, and that x is pronounced by. So when we read mxn, we actually say m by n. Okay? It's called an m by n matrix. This example right here is given as a 3 by 4. And those numbers, that 3 and the 4, m, that first number 3 in this case, represents the number of rows, and n represents the number of columns. So if you know the rows and columns, you know the size of your matrix. Okay? M rows, n columns. Okay? And then in those rows and columns, every single number that you see is an entry. Okay? An entry is just each value in a matrix, or each number in a matrix. Okay? So the values or the entries in this matrix would be 2, 3, -4, 6, 4, -1, 0, -2, 5, 7, -7, -1, 0. Okay? And every entry has a specific address, and an address tells the location. Okay? It's the location for a particular entry. Oops. So it's the location of each entry. For example, the entry for -7 would have an address of 3, 2. Okay? Not 3, 2. Yeah, 3, 2, sorry. -7 would have an address of 3, 2. Here's how it works. Every matrix is named with a capital letter. So for example, we could call this matrix A. And so when we write our address, we're going to take the lowercase version of the name. So if this was capital A, we use lowercase a. And then we use subscript. And the subscript is written as the rows first, and then the column it lives in, right? The row and then the column. A lot of times, you may see M and N written as I and J, but here we're going to just call them M and N because we've decided that that's our letter for rows and our letters for columns. Okay, so this comes from the name. What row does it live in? What column does it live in? So as we look up here, if we really want to zoom in on this -7, we can come up with its address. It lives in A, row 3, column 2. So it's A32. When you write the address, every entry has a different address. And so if you know the address, you can figure out what the entry is. If you know what the entry is, you can figure out the address. Okay, entry and address, it's a good way to be able to talk about them. Now, for matrices, we can do some operations. Oh boy, we can add and subtract matrices. Okay? But we can only add and subtract matrices that have the same dimensions. That's a key. They have to have the same dimensions. So for example, up here, A and B, they have the same dimensions. C does not. Okay? So just let's look at 3 quick examples. We can do A plus B. We could do B minus A. And then we could try and do A plus C. Okay? You're going to just add the entries. So for A plus B, here's matrix A, 3, 6, 5, 0. Here's matrix B, 12, 7, 5, 9. And when you add them, just add the corresponding entries. So in matrix A, A11 is 3. In B, B11 is 12. So we're going to add 3 and 12 because they're in the same spot, and that's going to give us 15. Okay? Now, 6 and 7 will make 13. 5 and 5 is 10. 0 and 9 is 9. Okay? So really, you're just adding the corresponding parts. 3 and 12, they're in the same spot, we can add them. And that's why matching dimensions is so important. Okay, B minus A. 12, 7, 5, 9 minus 3, 6, 5, 0. So we subtract the corresponding parts. So we're going to do 12 take away 3, well that's 9. 7 take away 6 is 1. 5 take away 5 is 0. 9 take away 0 is 0. So that's the difference of B minus A. Now, A plus C. A is 2 by 2. C is 2 by 3. This is impossible. Okay, the dimensions have to be the same. I'm going to say it again. The dimensions have to be the same for addition and subtraction. Okay? Addition and subtraction, same dimensions. Now we're going to look at another part, another operation we can do. And of course I have to wipe this again because it's driving me nuts, but that's okay. I'm looking at this, scalar multiplication. Scalar. A scalar is just a number. That's really all there is to a scalar. A scalar is a number. Okay? And you can multiply any matrix by a scalar. So for example, we can take and multiply C, that matrix, by a scalar of 3. We can multiply B by the scalar negative 1/2. A scalar is just a number that we're going to multiply. Here's how it works. You're going to love this. 3, 6, 9. Yeah, math's fine. Okay, here we go. So now we're just going to multiply. 3 times 3 is 9. 3 times 6 is 18. 3 times 9 is 27. It's like the distributive property on steroids. Truly, that's all there is to it. You just multiply everything. Boom! Done! How cool is that? I'm so excited. Okay, so, let's look at one more real quick. Here we have a negative 1/2 B. So, everything in B, in matrix B, is going to be multiplied by negative 1/2. Negative 1/2 times 12, negative 6. Negative 1/2 times 7, negative 3.5. Negative 2.5. And negative 4.5. Right there is the product of negative 1/2 and matrix B. Okay, so you're going to be practicing this. You're going to be practicing matrix addition, you're going to be practicing matrix subtraction, and you're going to be practicing the scalar multiplication with matrices. Okay? Now, that's kind of all the like plug and chug, the do it, make it happen sort of stuff. We have to talk a little bit about some of the more abstract stuff because there's a couple properties. Oh, boo. There's a couple properties here for matrices. So let's take a quick look at those. There's 4 of them I want to clue you into. And when I talk about these properties, I want you to note that they really only work for addition. When we get into multiplying matrices, and I mean more than just scalar, then the properties start to get funky. Okay? But in the meantime, commutative property. Hopefully you remember what the commutative property. In terms of numbers, commutative means that A plus B equals B plus A. Well, in terms of matrices, it means that matrix A plus matrix B, I'm just going to make them little guys, is the same as matrix B plus matrix A. You can switch the order on your adding. no matter which way you go about adding these two, you're going to get the same result. You're going to get 5, 7, 2, 7. I wish I could say it was more exciting. You switch the order, you're going to get the same result. The associative property, okay, in terms of numbers, it looks like this. And you could switch the parentheses. You could switch who we were hanging out with. You can do the same thing with matrices, okay? You can add together 2 and then add, and you can switch the order around, okay? These are just really little guys. Because, to be honest, order of operations still applies here. We would do the stuff in the parentheses first. This is going to be the same even if we do these two matrices and then finish with that. You're going to get the same result. No matter how you group your matrices A, B, and C. Whether it's B plus C and then you add A, or A plus B and then you add C. It's the associative property. Okay? Additive identity. In terms of numbers, any number plus 0 equals the number. Oh, whoops, my bad. Got the board freaking out. Okay, so 0 was the additive identity. In terms of matrices, the additive identity is the 0 matrix. It's a matrix where all entries are 0. Like, how cool is that? We also have something called the additive inverse. Okay, in terms of numbers, the additive inverse was the opposite. In terms of matrices, we have an additive inverse of a matrix. Okay? Each entry is the opposite. So for example, if our matrix was 5, -2, -3, and 1, our additive inverse would have all of them be the opposite. Instead of 5, we would have -5. Instead of -2, we'd have 2. Instead of -3, we'd have +3. And instead of 1, we'd have -1. Okay? Now, all of this stuff right here is getting to be a little bit more theoretical, but we're using a lot of those same ideas that we used with numbers. Now we're just applying them to matrices. We're just collections of numbers, arrays of data. Okay? Being able to add them, subtract them, and use scalar multiplication on them is going to be kind of key for what we want to do with them down the road. Okay? There is a way to plug them into your calculator. I will show you that in class. We'll make sure we got it. But in the meantime, make sure you know how to add, make sure you know how to subtract, make sure you know how to scalar multiply, and you will be good to go for 4.1.